Today we're going to talk about piecewise functions and even and odd functions. Continuing in chapter 1.1 in our notes. Remember, a function from previous years of math is a rule that maps x in the domain and that's called the independent variable. To the y value in the range. Domain and range. And the y value in the range is called the dependent variable. First of all, let's talk about piecewise functions. Piecewise functions, just like the name implies, is a function that's made of two or more pieces. And its definition changes depending on the value of the independent variable. And usually we have the independent variable called x. And what does a piecewise function look like? Well, piecewise functions start out with f of x is equal to, and then you have a bracket, and then the pieces go here. I'm going to show you a piecewise function with two pieces. Let's say f of x is equal to negative x, and that only happens when x is less than 0, so there's your independent variable. And f of x is equal to positive x, and that's when x is greater than or equal to 0. So depending on what's been input, what value of x, you're going to evaluate either this or this part. So for example, and this is called the absolute value function. And you'll see why in a minute. We're going to evaluate f of certain numbers. Let's evaluate f of negative 3. Well, negative 3 is less than 0. So we're going to look at this definition. F of negative 3, we're going to put the negative x value in here. Well, the negative x value is negative 3, which is 3. Let's do f of negative 60. Well, negative 60 is less than 0, so you're going to evaluate the negative input value. Negative 60 is positive 60. Let's do f of 0. Well, f of 0 is at the breaking point, but 0 is greater than or equal to 0, so f of x is just x, and x is 0 in this case. And let's do f of 5. Well, 5 is greater than or equal to 0, so f of 5 is just the x value of 5. So you can see this is absolute value, just the way all of these have come out to be positive values of the input. So here's another example. I should have put this as your big example. And let's say your second example, let's do another random piecewise function with two pieces. Let's say x plus 2, and that's only when x is less than 1. And let's say x minus 1 squared, and that happens when x is greater than or equal to 1. So we have a breaking point here of x is equal to 1. So whenever x is less than 1, let's evaluate a few things. Let's evaluate f of 0. Well, 0 is less than 1, so we're going to use this definition up here. So f of 0 is equal to 0 plus 2, which is 2. Let's do f of negative 3. Negative 3 is less than 1, so f of negative 3 is negative 3 plus 2, which is negative 1. Let's do f of 1. Well, 1 is greater than or equal to 1, so we're going to use this definition. So it is 1 minus 1 squared, which is 0. And then let's do one more greater than 1. Let's do f of 2. 2 is greater than 1, so f of 2 is equal to 2 minus 1 squared, which is 1. So you can evaluate this at any value of x, and depending on the input, you either choose this piece or this piece. Let's graph this. So if we wanted to graph this, we set up our xy axes. We notice that there's a breaking point of x equals 1 because that's where the definition changes. So x equals 1 here. We're going to put x equals 1 here, and to the left of x equals 1, we're going to graph the function x plus 2. Well, x plus 2 is a linear function with a y-intercept of 2 and a slope of 1, but that only happens when x is less than 1. So 0, 2 is on this graph. We've already figured that out. Negative 3, negative 1 is also on this graph. We figured that out when we evaluated this. Negative 3, negative 1. But when x equals 1, you're going to have an open circle because it is just strictly less than 1. Oops, if I could graph a little bit more accurately, that would be better. Well, anyways, this is supposed to go through, this is 1, 3, 0, 2, negative 3, negative 1. And then put an arrow on the end. So this is y equals x plus 2. That is the first piece. Now when x is greater than or equal to 1, you have a parabola. You have a quadratic that's been shifted to the right one. If you remember from Algebra 2, this is a right shifted parabola. So when x is equal to 1, we've already evaluated x is equal to 1, y is equal to 0. So there's a point on our graph. When x is equal to 2, y is equal to 1. So there's another point on our graph. If we try to find f of 3, 3 minus 1 is 2, and 2 squared is 4. So f of 3 is equal to 4, and there's our parabola, which is just a little bit curved. And this is y equals x minus 1 squared. That's the second piece of it. Let's look at a couple more piecewise functions. Third example, let's have a piecewise function with 3 pieces. Let's say f of x is equal to 3 when x is less than negative 1. Let's say it's equal to x plus 1 squared when negative 1 is less than or equal to x is less than or equal to 1. And let's say it's x minus 4 when x is greater than 1. So we've got all the x values defined here. Let's evaluate some. Let's evaluate f of negative 2. Well, negative 2 is less than negative 1, so no matter what, if x is less than 1, your output value is always a 3. F of negative 4 is also equal to 3. F of anything less than negative 1 is equal to 3, always. That's the first piece. Let's do f of 1. F of 1 is in this range. 1 plus 1 is 2, 2 squared is 4, so f of 1 is 4. F of 0 is in this range. 0 plus 1 is 1 squared is 1. And let's do a couple bigger numbers. Let's do f of 2. It's equal to 2 minus 4. 2 minus 4 is negative 2. And let's do f of 4. F of 4 is 4 minus 4, 0. So this is the first piece, just because of those input values. These two were the second piece, because of those input values. And these two are, I evaluated the third piece, because of those input values. So we've got first piece, second piece, third piece up here in our definition. And if we wanted to graph this, we just look at the breaking point. This has 2 breaking points in its graph. The breaking points are at negative 1 and positive 1. So we'll have x equals -1, x equals +1. And to the left of -1, the less than -1, f of x or y is equal to 3. It's a constant function. So this constant function, remember, is a horizontal line. And this is y equals 3. That's the first piece. The second piece is a parabola that's been shifted to the left 1. So its x-intercept is -1. Its y-intercept when x equals 0 is 1. And then when x equals 1, you've got y equals 4. So here's your second piece right here, and it stops right there because it starts at -1 and it starts at -1, stops at +1, just like the definition. So this is y equals x plus 1 squared. And then you have the last piece of x minus 4, and that's when x is greater than 1. So if you just quickly plugged in x equals 1, 1 minus 4 is -3. So you just have to put an open circle there because it's not defined there because x is greater than 1. But now this has a slope of 1. So we're going to just go up 1 over 1 for the next point, up 1 over 1 for the next point, and you can just connect that for your third piece. And this was y equals x minus 4. There's your third piece of the graph. So here's your piecewise function. None of these pieces connect. So you can see how that goes. We'll do some more practice tomorrow. Now let's do even and odd functions. First of all, even. A function is even if, number 1, f of -x is equal to f of x. 2, the graph is symmetric with respect to the y-axis. I'll say across the y-axis. And those two really, all three of these mean the same thing. For every point x, y on the graph, there is a point -x, y on the same graph. So for example, f of x is equal to the absolute value of x is even. Well, it's even because no matter what, if you put in an f of -x, you're always going to come out with f of x. Like if you do f of -3, f of -3 is always equal to +3. And the graph is symmetric with across the y-axis. I'll show you what the graph of y equals absolute value of x looks like. I think you might remember from last year. It's a V-shaped graph, and the points on absolute value are 0, 0, 1, 1, 2, 2, 3, 3. So it goes up this way. I could draw my points in a straight line. And then when x is negative, -1, +1, -2, +2, -3, +3 is the other part of the absolute value graph. So here's y equals absolute value of x. And you can see it's symmetric across the y-axis. If you folded it, it would go on top of each other. And for every point, like if you pick this point 3, 3 on the graph, then there's also another point called -3, 3 on the graph. If you pick this point 1, 1, there's also a point -1, 1 also on the graph. So this is an even function. Odd function. This is just an example of an even function. A function is odd if, number 1, f of -x is equal to negative f of x. 2, the graph is symmetric with respect to the origin. And I'll just put 0, 0 with respect to the origin, or in other words, it has 180-degree rotational symmetry. I'm sure you remember that from geometry. And then number 3, for every point x, y, there's a point negative x, negative y on the graph. And let's do an example of an odd function. Let's say f of x is equal to x to the third power. F of x equals x to the third power. Let's take a look at the graph of this. Sometimes it's best to look at a graph to determine if it's even or odd. Well, x cubed has 0.00, 1, 1, because 1 cubed is 1, 2, 8, 2, 3, 4, 5, 6, 7, 8. So the right-hand part of the x cubed looks like this. This is 2, 8. This is 1, 1, and 0, 0 is on the graph. Well, if you go to x equals -1, -1 cubed is -1, and -2 cubed is -8, 2, 3, 4, 5, 6, 7, 8. So a cubic graph looks like this, y equals x cubed. And you can see that f of negative x, if you have an input of +1 and you change that to f of -1, f of -1 is equal to negative f of x. Well, if x is 1, f of x is 1. If x is -1, negative f of x is -1. So this is one way. And the rotational symmetry of 180 degrees, that just means, you remember this from geometry, I'm sure. If you turn this upside down, it's exactly the same thing as it was right side up. So that's your 180-degree symmetry. And for each x, y, 1, 1, 2, 8, there's also a point -1, -1. -2, -8 are also on the graph. So that's always the case for y equals x cubed. Now, just to wrap this up, most functions are neither even nor odd. Most of them are neither even nor odd. For example, if you have y equals x cubed plus 3, you might think that would be odd, but x cubed plus 3 would look just like your x cubed graph, but it's been shifted up 3 units on the y-axis, or overall it's been shifted up. So x cubed plus 3 is a cubic shifted up 3, and it would look like this. Now this point right here, well, this point is 0, 3. This point right here is 1, 4. Well, -1, -4 is not on this graph. In fact, this point right here is -1, 2. So you can see that this doesn't hold just because you've got an odd exponent or whatever. This is not an odd function. And we're going to be talking about a whole bunch of functions and trying to classify them as even or odd. But that'll be tomorrow. So have a good night.